morning class and welcome to our continuing lectures on sustainable energy technology. We have been discussing various types of storage technologies so far, and today we will continue that theme. In the previous class, we discussed the storage of thermal energy or heat energy, especially different ways in which high temperature thermal energy can be stored in terms of hot water, steam or molten salt. But often in refrigeration and air conditioning systems, we need to store thermal materials at temperatures lower than the ambient. This is especially useful to serve the demand of increasing air conditioning needs during the summer months, which create peak energy demand in the afternoons, as we have seen multiple times before. That if you look at a hot and sultry summer afternoon or early evenings during a summer month, you will see an extremely large rise in air conditioning and cooling demands both from domestic users and office and industrial users. So for this aspect, it would be very convenient if we could store materials at a temperature lower than the ambient during periods of low demand, that is late nights or early mornings, and use this cold material to supply some of the cooling needs during the periods of peak demand. So this is what the storage of coolness seeks to achieve. The popular materials used for this storage of coolness is like chilled water, which is usually stored at 5 to 10 degrees centigrade. Mixtures of water and ice, this will be at 0 degree centigrade, and frozen salts that can be stored at temperatures below 0 degree centigrade. So if you want moderate cooling needs, then chilled water, which is cooled to 5 to 10 degrees centigrade and stored at that temperature, will do. For higher cooling needs, you can store a mixture of water and ice at the freezing point, that is 0 degree centigrade. And if you want significantly greater cooling needs, for example industrial refrigeration systems, then you may store frozen salts at temperatures below 0 degree centigrade. So here a typical process when we are looking at chilled water is you are cooling water using air conditioning systems during off-peak hours and storing this chilled water in insulated tanks, then circulating this chilled water through the buildings during peak hours to cool them and reduce the air conditioning demand. So the idea here is, just like space heating, you can have space cooling. You have ducts in the buildings through which this cold water that has been cooled to temperatures of 5 to 10 degrees during off-peak hours, and this cool water is flown through the walls of the buildings during peak hours, for example a residential unit or an industrial unit or an office space, and cool them, and this will reduce the air conditioning demand of these office spaces or domestic spaces. An example of this is chilled water tank used to reduce AC load in the Dallas airport in USA. So Dallas airport is located in a region of US which becomes significantly hot in summer. Okay. So this chilled water tank in Dallas airport can store over 100,000, so 60 lakh gallons, that is 22,712 meter cube of chilled water at an average temperature of 8 degrees centigrade. This is capable of delivering 90,000 ton hours of refrigeration capacity. So if you look at a refrigeration air conditioning system in common markets, you will often hear the term as 1 ton, 1.5 tons, 2 ton air conditioning. So these kinds of systems are basically saying that it is a kind of a measure of the capacity that refrigeration or air conditioning system has in cooling a certain space. So higher the tonnage, greater the ability of that air conditioning or refrigerating unit to extract heat from a region. Okay. So this chilled water of 60 lakh gallons is capable of delivering 90,000 ton-hours of refrigeration capacity. So a refrigerator, 90,000 1-ton refrigerators working for 1 hour. That is the amount of refrigeration capacity this chilled water can give to the Dallas airport, and this is equivalent to the ability to extract around 1.14 to 10 to the power 12 joules of heat from the airport system. The chilled water is produced and stored between 12 am and 6 am when the airport is usually closed, and is used to cool the airport during working hours, which is 6 am to 12 am. So this is an established commercial system which basically is helping to reduce the electricity demand during the peak hours for an extremely busy international airport. Just like chilled water, ice can also be used to store coolness. Ice formation helps in increasing the cooling capacity as the latent heat of fusion is absorbed by ice as it melts. So just like steam, when steam is condensing, it is releasing heat to the system, and hence steam is extremely useful as a medium of heat, storing thermal energy at high temperatures. Similarly, ice, when it melts, absorbs the latent heat of fusion from the surroundings, and hence ice is a very good medium to absorb heat from a system. Okay. So ice can be used as the storage medium for coolness and can be used to cool the circulating water for air conditioning purposes, and the melt water itself can then be circulated to further cool the buildings. So if the capacity is high, the cooling requirement is high, you can directly use air conditioning systems in off-peak hours to create ice, and then this ice can be put in a heat exchanger and can be used to cool the water that is circulating through the buildings during the peak hours to reduce the air conditioning demand. Then heat will be absorbed by ice from the circulating water, chilling the water to low enough temperature that it reduces the air conditioning device. And as the ice absorbs this heat, it melts. And this melt water itself can be added to the circulating water system and further increases the cooling capacity that this storage medium has. For example, a company called Ice Energy is installing around 1200 ice thermal storage units with cumulative 21 megawatt capacity of cooling in Southern California. Southern California again is a part of US which gets quite hot in summer, and here this company is installing 1200 such ice thermal storage for various industrial and commercial applications which have a cumulative power rating of 21 megawatts of thermal cooling energy storage capacity, and this is being installed in various parts of Southern California, which is a state in USA. So with that discussion of thermal storage, we are kind of coming to an end of the various types of energy storage technologies that we have discussed. We have looked in detail about the various technologies, how they are used, their key advantages and disadvantages. So now in this class and probably going to the next class, we will look at all of these technologies together and how they are used in creating a modern grid with large renewable energy penetration. So here we will look into a synoptic or an overall view of the energy storage technologies that we have looked at and how they are used in a modern grid in today's world. Now, what are the storage needs of a modern grid? There are many different functions that an energy storage technology can do in a modern grid for various storage requirements. The first type of storage requirement is arbitrage or storage trades. So this is storing low priced energy during periods of low demand and subsequently selling it during high priced periods within the same market is referred to as storage trade. Similarly, arbitrage refers to this type of energy trade between two energy markets. So consider an Indian state grid. Okay, so for example, a grid in Uttar Pradesh or a grid in eastern India, etc. Now, suppose you have a storage technology that is installed in a location whose function is to store low priced energy during periods of low demand, that is late night or off peak hours, and then selling this energy back to the grid at periods of high price, that is high peak during periods of high energy demand. This kind of trading of energy, extracting energy from the grid at a low price, at low demand, and then selling it at a high price during periods of high demand is called arbitrage if it happens within the same grid. What this helps is, firstly, it gives a financial incentive for the storage industries to develop such storage technologies, and it also helps to balance the demand supply. Prices are high during periods of high demand because the supply is low and the demand is high. So if storage units are incentivized to transmit their energy during this high demand hours, then of course the supply will increase. So this kind of a commercial structure helps for the grid to balance its energy versus demand, and it also helps the customer to decrease its energy cost because there is more supply, so the cost will decrease overall. Similarly, arbitrage refers to this type of energy trade between two different energy markets. So if one state grid is selling to another state grid, etc., then this is called arbitrage. It's the same thing, it's just a different technical term because you are between grids, the purchase and buying is happening rather than within a certain grid. Another type of application for storage is frequency regulation. So the balancing of continuously shifting supply and demand within a control area under normal conditions is referred to as frequency regulation. So this is basically what is regulating the AC current voltage frequency or the AC current voltage, right? So it's regulating the frequency by balancing the supply versus load. Okay, and this is done on a real time, minute to minute, second to second basis. So management is frequently done automatically on a minute to minute or shorter basis. So energy storage needs that look into frequency regulation by giving when there is a sudden supply demand mismatch over a short time scale, it pushes some of the energy to increase the supply so that the frequency does not drop, right? So that's the idea. And if there is a sudden increase in supply compared to demand, it extracts that energy to again balance it back. So this quick injection and absorption of electricity from the grid is also an important aspect of storage technology. And this is called frequency regulation, and as you can understand, this is for this type of storage systems do not need long periods, but it has to be fast response, low capacity but high efficiency systems. Okay. Then another very common usage of storage systems is demand shifting and peak reduction. So energy demand can be shifted in order to match it with supply and to assist in the integration of variable supply resources. So here we are actually trying to shift the energy demand from a peak hour time to an off peak hour time so that the change in the demand, rapid change in demand does not happen. Okay. These shifts are facilitated by changing the time at which certain activities take place. So this is demand side changes, okay, in either behavior or technologies. Arbitrage or storage is trying to balance the supply side, okay, whereas demand shifting is trying to change the usage or technology to change the demand side, again to decrease the peak versus trough differences in energy demand. example, when the heating of water or space is taking place. So if you have a localized chilled water system that is reducing the demand of air conditioning in an office by transporting chilled water to the walls, as we just discussed, that is decreasing the demand of that housing society or industry to extract electricity to run its ACs. So that is demand shifting. Similarly, in winter times, in cold winter nights, if you are using a space thermal energy storage system for space heating during these cold winter nights, then also you are requiring less electricity from the grid to heat up your buildings during these winters. Okay. So that is again shifting the demand. Okay. So these shifts are facilitated by changing the time at which certain activities take place and can be directly used to actively facilitate a reduction in the maximum energy demand level, as we just discussed. Okay. Another very important application is load following, the second continuous electricity balancing mechanism for operation under normal conditions. The first is frequency regulation, the second is load following. Following frequency regulation, it is load following. Load following manages system fluctuations on a time frame that can range from 15 minutes to 24 hours. So these are medium time scale changes in the supply side and can be controlled through automatic generation control or manually. So this is basically like turning on or turning off cycling or peak power plants to increase the supply to track the load. Okay, so this is basically the load following mechanism. Peaking power plants, cycling power plants that are being added on during periods of high demand is basically an example of load following. Okay, so you are adding extra capacity during periods of high demand and then again turning them off during periods of low demand so that you are able to match the load that is coming during a period. And this is load following can range from 15 minutes operation to 24 hours operation as well, depending on the requirements. But that is the usual time scale. So while frequency regulation is minute to minute, second to second changes, load following is like an hourly, 6 hours, 2 hours, or even a day kind of a change in demand, change in supply to catch up with the demand. So this is AC current frequency, this is load changing, and then finally the voltage support. So frequency regulation and voltage support are related to each other. This is the injection or absorption of reactive power to maintain voltage levels in the transmission and distribution system under normal condition is referred to as voltage support. Okay, so you are basically changing, responding to keep the voltage levels constant. Spinning and non-spinning reserve is another technical term. So here the idea is quite simple. Suppose you have a grid that is working and suddenly one power plant malfunctions, it stops working, or suddenly it's the amount of energy it is injecting decreases suddenly under unforeseen cases. But the demand is there, right? So you have to have a reserve from which you can draw in order to compensate for the sudden loss of that power plant's energy generation capability. So these are called reserves that a grid must have to tackle such unforeseen changes. Okay. So reserve capacity for electricity supply is used to compensate for a rapid unexpected loss in generation resources in order to keep the system balanced. This reserve capacity is classified according to response time. So how fast this response can happen from the reserve. Spinning reserves have less than 15 minutes response time. So suddenly if there is a drop in supply, a spinning reserve can turn on within 15 minutes. So rapid response reserves. And non-spinning reserves are greater than 15 minutes response time. These are slow to respond to sudden drops in supply. Okay. Faster response times are generally more valuable to the system for obvious reasons. In some regions, reserve capacity is term referred to as frequency containment reserve. Okay, so that is kind of controlling the frequency, not letting the frequency go out of hand. Okay. You need both spinning and non-spinning reserves. Spinning reserves are usually costlier because it's fast response, and once the non-spinning reserve becomes active, the spinning reserve is taken out of commission, because the non-spinning reserves are, even though they are slow to respond, they are usually giving cheaper electricity compared to spinning reserves. Okay. So first the spinning reserve kind of contains the problem, and then the non-spinning reserve gives a more permanent solution till the main power plant can again come back in operation. Now these spinning and non-spinning reserves can be energy storage technologies, it can be reserve power plants, etc. And they are very useful in a renewable energy grid, because suddenly if the wind goes to zero, your wind farm suddenly stops giving any power. So you need this kind of a spinning and non-spinning reserve to take up the slack till the wind returns. Okay. Then you have a important but rarely used type of energy storage, which is black start. So this is in a rare situation where the power system collapses and all the ancillary mechanisms have failed. Black start capabilities allow electricity supply resources to restart without pulling electricity from the grid. Okay, so these are standalone emergency systems that start running when all other systems have failed. So there is a grid failure that is imminent, that the entire grid can come out of reckoning because all the other fail-safe mechanisms have stopped working or has proven ineffective. Okay, so this can start the grid from the beginning. It can reboot the grid and give the initial resources necessary to restart the grid and put it back into operation. So these are called black start reserves. A very important and emerging area is variable supply resource integration. This is directly aimed at renewable energy integration, because renewable energies are variable supply resources. The sun does not shine all the time, wind is not blowing at constant velocities, hydropower is seasonal, so all of these are variable supply resources. The use of energy storage to change and optimize the output from variable supply resources, example wind, solar, mitigating rapid and seasonal output changes and bridging both temporal and geographical gaps between supply and demand in order to increase the supply quality and value. You understand the temporal gap. So for example, wind is blowing very strongly at night when there is late night, when there is low energy demand. Okay. And it stops blowing, suppose in the afternoon, in a hot humid afternoon when there is a high energy demand. So there is a excess capacity at night and lower capacity than demand at daytimes. So there is a temporal gap between when the supply is and when the demand is. So that can be bridged by energy storage systems. Geographical gaps are gaps between where the demand is and where the supply is. So for example, offshore wind, nobody lives on the ocean obviously. So how do you transport the electricity generated in an offshore location towards the coast to a more or less densely populated location? Similarly, onshore wind farms are also often placed in mountains. Similarly, hydropower plants are present in where the river is descending from the mountains, and these are usually thinly populated. So for example, the Three Gorges Dam is in Tibet, whereas most of China's electricity demand is thousands of miles away from Tibet. So how do you transport that electricity from the place of generation to the place of supply? So that is the bridging of geographical gaps. You can create storage facilities and transport that stored energy through multiple stations back towards the central grid. Finally, of course, off-grid storage is an important aspect. Off-grid energy consumers frequently rely on fossils or renewable resources to provide heat and electricity. To ensure reliable off-grid energy supplies and to support increasing levels of local resource use, Energy storage can be used to fill gaps between variable supply resources and demand. Consider a remote location where there is a mountain stream and you have a small hydropower plant there. You can use that in conjunction with an energy storage system to deliver power to those villages even when during periods when the river is running dry, or a small local wind farm. Again, an energy storage is required to generate to give a continuous supply of electricity to the local villagers because it is not connected to the grid. So there aren't any other alternative supplies of energy that can be used when the wind stops working, right? Similarly, solar farms, off-grid solar farms. At night, you need something else to run those electricity bulbs, lights, etc. Okay. So we will stop here. These are the many ways in which energy storage can be used in a grid, and we will look at the various energy storage technologies we have covered and some we have not covered in detail because there are many types, and we will see what is most useful in the next class. Thank you for listening, and we will see you back in the next class.